Okay, we are recording. So we can start, I think. Good afternoon, everybody. It is a pleasure to have with us Padre Gabriele Gionti from the Vatican Observatory. Let me briefly introduce our guest today. Padre Gabriele got his PhD in quantum gravity in 1998 at the SISSA in Trieste after graduating in University of Naples. As a postdoc, he had different positions at the University of California, Irvine, then at the Vatican Observatory and Stewart Observatory at the University of Arizona. Then in 2000, he entered the Society of Jesus. You probably know now. And after following his ordination in 2010, he pronounced his final vows in the Society of Jesus in 2019. Yes. And since 2010, he is permanent at the Observatory, the Vatican Observatory, and since 2022 is deputy director of the So his research is on cosmology and quantum gravity with a specialized focus on mathematical foundations of the universe. In particular, only a short list I've taken from his CV: alternative theories of gravity and T-duality in strings theory. But among the other things that is an expert today is going to talk about why we still can model our universe, a guide to quantum gravity.
Yes.
Microphone is yours. I give you.
Thank you, Mike or me? Michele. Thank you, Michele, for the invitation to all of you. I tried to explain many times to my brother Jesuit quantum gravity, and I always was unsuccessful. Also because the field is not closed and it's not clear. There are many issues that I will try to explain again. Hopefully, I will be more successful. But okay, I will try to communicate the main idea because the mathematical behind is quite complicated. So many different we start with 1915, the publication of the Einstein general relativity. The paper of Einstein general relativity was submitted or published, I don't remember where, and the author was Albert Einstein, but the action of the gravitational field was contemporarily done also by David Hilbert, this person was a mathematician. And in the same year, Emmy Nader, this lady who unfortunately died in concentration camp because she was Jew, did the conservation law of in field theory and in classical mechanics that has been used also in generative. But credit of this first slide is to Maria Felicia de Lorenz because she lended me twice.
So from remote, they're asking if you stay closer to the micro.
Closer to the
to
the micro to the.
If you stay on the side, that will be fine.
Side here.
See. If you move too much,
okay.
Won't hear.
What is general relativity in few words? Main ideas is an extension of special relativity. You mean deals with non-inertial reference frame, means two reference frame whose relative velocity is it's not constant, it is an acceleration, and this is one of the reasons for which Einstein formulated this general relativity, and is based on fundamental principle, the equivalence principle, the mass equivalent. The gravitational mass is numerically is the same, it's equal to the inertial mass. I mean, the way in which two bodies attract each other is the same quantity of the opposition that the body will put to a motion. So as a consequence of this equivalence principle, locally, gravitational effects are indistinguishable from acceleration effect. What does it mean? That if I have a starship that is accelerating with velocity g, in the starship, an apple, a free-falling apple, will feel a gravitational attraction towards down that is g. And that is the same gravitational attraction that an apple will feel if you lift the apple and you are on Earth in the starship. And an astronaut in the space will feel without any massive body will feel no gravity, like an astronaut that is on Earth in the starship while the starship is free falling on Earth. So because the acceleration effect in the starship there is no gravity because free falling, so the apple will stay together with the astronaut. Now, there is a corollary to the principle of the equivalence that is very important, and is that the covariance principle is very important. The physical law in general relativity are the same in every reference frame. In every if you have two reference frame, one respect to the other that is accelerating, while you know in special relativity you have to have constant velocity, otherwise the law will change. Here the law are the same in every reference frame. Also, in the case in which two reference frames are accelerating one with respect to the other. Okay. Now, the problem now is that with this assumption will follow that space-time, it's not anymore, it's a physical entity. It's in general, also in particle physics, the space-time is like a stage in which phenomena will happen, and the phenomena will not modify space-time. Now it's not this way anymore, because the presence of massive body or energy will modify space-time, creating curvature. So if you have a ray of light, this ray of light is deviated by the curvature because we'll feel the curvature of the massive body and will be deviated. So you don't see the star where it is, but with this deviation, as you know, you are an astronomer, and so you know that to me that you have this gravitational lensing and you have the stretching because of the fact that there are massive particles. And this is important, the last line. Gravitational force is not anymore an action at distance like in Newton's law, the Newton gravitational law, but it's a field theory because it propagates with the same velocity of light, like electromagnetism, the gravitational force. These are, if you have already seen somewhere, probably the gravitational action that is called Einstein-Hilbert action. You have okay, it's complicated, but it's the first term plus a boundary term. And the Einstein equation are these tensorial equations that are 10 independent equations for first class constraint. Is technical. First class constraint means that you have the 8 constraints. So at the end, you have 2 degrees of freedoms. And in fact, the graviton is a supposed particle that should be the particle of the gravitational interaction has 2 degrees of freedom. Spin up and spin down. That's it. But the spin is 2 now for graviton. Now, one of the problems of Einstein general relativity are singularities. Einstein general relativity is plugged with singularities, sorry. You have Big Bang singularity, I mean, at the beginning of space-time, so you have a singularity, the equations are divergent. And you have singularity with black hole, the black hole singularity. You have also other kind of singularity that are called the naked singularity, etc. So the solution of Einstein equation are plugged with singularity. This is a signal, we think, that the theory does not work well close to the singularity. This is what happens in other cases. But unfortunately, we do not have any signal or phenomenon that could say something about this fact. But if we phenomenologically, if you put together some constant, the Planck constant, the velocity of light, the gravitational constant, the Boltzmann constant, you got what is called the Planck temperature. That is a quantity. You can build with this constant the Planck mass, a mass. You can Planck times the Planck length. And we always phenomenologically we say that up to the Planck time or to the Planck length, between 0 and Planck length, probably there should be this period of the universe in which the universe, the gravitational laws and the were quantum mechanical. I mean, the way of behaving of the gravitational field was not classical like the other classical interaction, like electromagnetism, but probably of quantum nature. But up to now, nobody has been successful to find the right theory, also because we don't have phenomena with which to test the theories, or the theories, because there are many theories. What we know is the Einstein general relativity is considered a successful phenomenological theory at laboratory, solar system, galactic, for a scale above the Planck length, that is of the order 10 to the minus 33 centimeters. So above this fundamental length, Einstein general relativity works for. And also the gravitational waves is confirmed that the Einstein general relativity is not alternative theory, it's better than other theories. The singularity problem that I have shown, and also and the fact that the matter behaves quantum mechanical. So since the matter itself is quantum mechanical, since in the second term of the Einstein equation you have the energy momentum tensor, that is the matter, would be a contradiction. This is an observation that I found in Landau, this book of Landau. Would be a contradiction to the second term is quantum mechanical, the first term is classical. They should be both quantum mechanical. So there are also these objections. So at very small distance, that means at very high energy, the gravity should be quantum mechanical. There are many different approaches we have developed up to now, and there is no agreement among the different communities. There is a string theory that probably you have heard that is more famous, not successful, but famous. Loop quantum gravity, non-commutative geometry, dynamical triangulation, causal asymptotic safety, and so on. Okay. Particle physicists would say that general relativity is considered an effective theory, not a fundamental theory, because the gravitational constant it's dimensional in natural unit. Natural unit is when C equal H bar equal G equal 1. Yeah, this is a very theoretical way of thinking. Everything is working well. I mean, so you have to find what are the new fundamental units. So in these fundamental units, the gravitational constant has a dimension of a length to the minus 2. So this means that the theory is not renormalizable or perturbative. It means if you do expansion of the theory, quantum mechanics, you don't are able to renormalize, to eliminate the infinities with the contact. I will explain this later. Okay, I would like to, since you said a small recap of the fundamental thing of analytical mechanics. You have seen a Lagrangian. Lagrangian is something that is defined as the kinetic energy minus the potential. You define a new variable that is called the momentum, that is the same momentum you have in physics, but now it's a variable, and you define the Hamiltonian. The Hamiltonian now is a function of the momentum, the momenta, and the positions. With this, and you have this is the phase space in analytical mechanics, and on this phase space you have what they call Poisson bracket among function on this phase space that have this definition. You remember probably from analytical mechanics, and the Poisson bracket among the fundamental variable among object have this property. Very simple. If you put here, you find it is 1 or 0 and so on. But why this is a recap is important? Because this is, as you know, when you've done elementary quantum mechanics, you see that the Hamiltonian approach is the way we used to quantize. Because the momenta becomes an operator on the Hilbert space according to the Dirac map, and the position becomes an multiplicative operator on the wave function. The Poisson bracket commutator among operator in the Hilbert space. This wave quantized. We don't know why, but it works. And so the Poisson bracket is the commutator. So the commutator among the fundamental variable on the space on the wave function is this quantity, and you know, the same thing of the Poisson bracket and so on. But why I told you? Because the way we quantize in the hydrogen atom is to solve the Young-Value equation on the wave function. That gives you the energy, and after you determine the evolution of the wave function, and in this way we were successful in solving the spectra of the hydrogen atom, because we were able to solve the Schrödinger equation. And we have the spectrum of the hydrogen atom, and so we are able to explain why you have the absorption line in the spectra of the hydrogen atom. And you know that the energy is this energy is quantized and so on. This is what. Okay. The main idea: could we do the same for the gravitational field? I mean, if it works for the hydrogen atom, the idea is applied to the gravitational field. And it has been done. Okay, no, before this, probably this you have not seen. You have heard something about the Feynman path integral. There is another way to derive the evolution of a quantum system without the Schrödinger equation. This was found by Feynman in his PhD thesis. If you want to calculate the probability that you have a system at the time Ta at position OA, and you want to find the probability that this system will be the particle at time TB and position QB, you have to calculate this integral, this Feynman integral, over all the possible classical line that connect these two position in the phase space. And you calculate this integral, and it gives you the probability of quantum mechanics probability that the system pass from one point to the other point. It's a mathematical procedure that is the same like shading equation, but that works because it has been that works for the quantum oscillator and for other simple systems. And it's the more used in field theory because it's sometimes better to write the Feynman path integral, as we're going to see, than to solve the Schrödinger equation. It's more complicated. And it can be also implemented numerically because it's an integral. You have to do sum. Now, so for a while, let's concentrate on the canonical approach, Hamiltonian approach. In the Hamiltonian approach, what we consider is a three-dimensional surface that evolves in time. So you have a surface in space-time that is a space surface that evolves in time. And at each time we have a foliation. This is called the ADM approach because it was the Hamiltonian approach to Einstein generality. It was formulated by Arnold with Desser and Missner. It's so the goal of this approach is to write an Hamiltonian theory for Einstein general relativity. And after writing the Hamiltonian, quantized, like the hydrogen atom. And this can be done, and what they wrote, it's the Wheeler-DeWitt equation. Wheeler and DeWitt separately, they wrote the Hamiltonian and quantized the Hamiltonian for gravitational field. Okay, the Hamiltonian is complicated because the Hamiltonian the Hamiltonian density is that formula. This is the momenta. You have to impose a commutation relation between position and momenta for the gravitational field. Are complicated. And in the end, what you find is an equation for the wave function of the universe. So all the universe has a wave function, and you try to solve this equation, but it's an operatorial equation, and nobody has never been able to solve. Okay. But there were people like Hawking and Hartle who had the idea why we do not solve this equation in particularly highly symmetric case like special solution of the Einstein equation like Friedman and Robertson Walker. So they restrict the Wheeler-DeWitt equation to very symmetric space solution of Einstein equation and wrote this Wheeler-DeWitt equation on this particular solution. So this is called quantum cosmology. It's not anymore quantum gravity, it is a higher level, but a lower level in which you assume that there is a special symmetry that comes from the Einstein equation. And probably you have heard that Hartle and Hawking found a solution of this Wheeler-DeWitt equation. It is called the Hartle-Hawking boundary proposal. Okay, they proposed the model of the universe in which the universe emerged from a state that is the vacuum, that is a Euclidean state, a state in which the metric is not anymore Minkowskian, but it's Euclidean, up to the Planck time. And above the Planck time is Lorentzian, takes again the old signature. So they eliminated the singularity in this way, considering a compact surface at the beginning. They say that they eliminated the singularity of Einstein general relativity. So the quantum process eliminates singularity. But there is a trick in all this way of reasoning due to the fact that this is a toy model. It's not the general solution of Relativity equation. It's a toy model that works in these cases. It's very particular solution of a particular toy model. And anyway, it's interesting because the space-time emerged from a vacuum state. And this vacuum state was a state without singularity. And people are happy with the solution. And the singularity that we hope that quantum mechanics will eliminate is really eliminated in this way. Loop one, you heard about this approach, loop one gravity. It's an approach that is based on the variable introduced by a relativist quite famous in the US, Abai Steger, who introduced the Steger variable, famous in the past, but was famous because this approach was developed also by Carlo Rovelli and Lee Smolin. And essentially, the idea is to write the Wheeler-DeWitt equation in a new set of variables in which you do a sort of an extension. And you consider, okay, it's technical. It's instead an invariant under the rotation group, you consider an invariance locally under a group that is the same group of the spin. So you find that the space-time is like a field with a loop of the spin group. And you have a loop of the spin group that fill the space-time. This was not really an idea of Rovelli Smolin, but dates back to Penrose. In fact, the original idea came from Penrose of filling space-time with spin networks coming from the same spin group that you use in quantum mechanics for the spin. And you have to define this holonomy matrix on these loops. And you have to define also function, function on these matrices. And function on these matrices, they found that are solution of the Wheeler-DeWitt equation in this Steger variable. So they say that the space-time looks like made out from this spin network, this object. So spin of networks of spin, sorry. And in this approach, it comes out that the area of space-time, not the volume, is quantized, is a discrete. And they have mathematical problem on which I don't want to say more because the Hamiltonian constraint, that is an object used in the Wheeler-DeWitt equation, it's not closed, so they have technical issue that they're not solved. But the important thing is that Bexton and Hawking in the 70s, they have found that the black hole horizon has an entropy that goes like the area. And these persons, I mean, especially Regge and Swaney, they found that you can reproduce this black hole entropy using loop quantum gravity. You got the same number of black hole entropy. This is an important result. But, okay, since they have a mathematical problem, especially Rovelli has developed also another formalism that probably you have had, spin foam, a foam made out of these spin networks, because they know, since the Hamiltonian constraint is not closed, they have to find a trick in order that the spin network evolve in time, and they consider this evolution happens in a discrete way. So they created this spin foam, the spin network that evolved in time. Okay, it's a technical thing and not very conceptual important. But so this is one approach to quantum gravity, is a canonical Hamiltonian approach. I have already mentioned, these are Feynman graphs, so probably in which essentially you describe the scattering of particles. And if what in general people think that the fundamental particle related to the gravitation should be the graviton. The only problem is that, as I mentioned before, gravity is not perturbatively normalizable. What does it mean? In theories that are considered by particle physicists fundamental, in general, you have infinities when you do the quantization through the quantum field theory, because you have infinities due to the fact that the way of quantizing in quantum field theory, you have it emerges that you have some problem with infinities. There is a way to get rid of these infinities, to redefine the mass, the electron charge fundamental constant, adding also counter terms, I mean extra terms in the action, in such a way that the theory becomes finite. It's not anymore, it's a mathematical trick. But in general, in theory that are perturbatively normalized, but the number of terms you have to introduce, it's finite, a finite number. So you have to introduce finite parameters in order to renormalize the theory and everything works. When the theory is non-perturbatively normalized like gravity, the number of contact terms you have to add is infinite. So you don't have anymore a predictive theory, because you don't control the number of parameters. So it's divergent and cannot be normalized perturbatively. So we know, as I said before, that gravity, if you do perturbation, it's not normalizable. So Hamiltonian approach works very well because it's not perturbative, so it's but complicated to solve. If you apply technique of quantum field theory, which do perturbation, doesn't work because it's perturbatively non-normalized. But in the end of 70, this person, in Italian, Gabriele Veneziano, found an interesting model. It is called the dual model, that was able to explain a problem in strong interaction. The duality of two channels in scattering theory. And later, other people, Nielsen, Ambo, and Susskind, they found that this model essentially physically could be interpreted like the fact that two quarks were linked like by a spring. And the confinement of quark could be explained with this spring that will keep the quarks together. this spring was like a one-dimensional string. And it was able to explain mathematically why the quarks were always confined and cannot be separated. The problem mathematical at that time was that they have a problem because were emerging some particle with negative energy that were called tachyons, that they go faster than light. And there was a strange spin to massless particle that they didn't know what it was. And the theory worked only in 26 dimensions because of mathematical problems called conformal motion. Okay. So later they understand that this strange object that was spin to massless could be interpreted like a graviton, the fundamental particle of general relativity. The fundamental particle. So all the industry, I call it, of string theory started. Because they say, oh, we can quantize Einstein general relativity with the string, unifying all the fundamental interaction in one interaction, which is called string. No, strings are considered, this is the mathematical action, but strings could be a one-dimensional object that can be open and closed and are more fundamental than particles. Because we have particles, string. Quantum oscillation of strings will give you the particle, the spectrum of the particle. This is a very good mathematical result. We don't know whether it's physical. The only problem is boson strings works only in 26 dimensions. It means that the string should be immersed in a space that is 26 dimensions. Otherwise, it does not make sense. And the theory is unstable because of the tachyons, this particle that have a negative energy. And you can, like, if you have particle, you can do scattering of particle, and now you can do scattering of strings, like particle, like of more fundamental object, and you can calculate this scattering analytically. And the theory is renormalizable, and it's finite. So this was the great success of string theory. And they say that they can re-get all the fundamental particle, the standard model, everything. So this is, it's really, in some sense, the theory of everything. If you couple string theory with supersymmetry, means supersymmetry is, as you probably have heard, is a symmetry in nature that has not been found yet, as you know. Because they claim that for every boson, there is a fermion. They should be in pair. And if you apply this symmetry to string theory, you get superstrings. And superstrings are better than strings because now you need only 10 dimensions. Okay, you save some dimension. And you don't have tachyons. The theory is finite, but the problem is supersymmetry has not been found at CERN, although they try many times to find something. Nothing came out. So this, the fact that there was this failure, let's say, was essentially also the reason for which string theory went down recently. There is another approach to gravity. Sorry, explain all the approach so you have a general idea. An approach to gravity that comes from another Italian that is called, you probably read, Tullio Regge. Essentially, he proposed a sort of general relativity, not on continuous manifold, but on manifold surfaces that are triangulated with triangles. If you join together triangles, like in a Lego game, you can get a surface. And you can calculate a curvature of the surface locally. You can calculate an action. You can derive the equation of motion. But the original idea of Regge is that in this way, you can do numerical simulation. Because you do gravity, you can implement numerical simulation. You have a surface that is called the simplicial complex, so to say, that is a triangulated surface, and you vary the edge length, you vary also the different type of triangulation on the surface. The problem is that when you quantize this, you in general, what people do is to quantize this theory with the path integral that I said at the beginning. You put in the path integral and you quantize the theory. The problem is that this measure, the quantum measure, is quite. I'm working on that, on the quantum measure of Regge calculus now, because you don't know each configuration with what is the weight that you have to put in each configuration when you do the sum. Why? Because as you oh, there was a time. There was a limit. Okay, so because this is a variant of Regge calculus. It's called the dynamical triangulation, in which the triangles are equilateral. And this has been more successful with numerical simulation, because in this way, they found that in the phase space of dynamical triangulation, when you have gravity very strong, it happens that you have few vertices, and all the triangles are incident on this vertex, and means that you have a very singular geometry. So close to the Big Bang, gravity is very strong and attractive. When you go beyond this critical point, gravity is very weak, and you have a situation of branch polymer in which the curvature is very low. So gravity is very weak. So they show that close to singularity, you have a very strong oscillation of gravity. It's very strong gravity. So it seems that numerically works. Okay, this is my, it's not still clear what is this measure. They put a measure without, and they do simulation without really knowing where it's right or wrong. Okay, this I can do. This is a way to calculate the measure. You calculate the determinant is phi the Popov determinant. Okay, this is a final approach is asymptotic safety that has been developed since the second half of the 90s. And it comes from an idea of Steven Weinberg. I told you that gravity is not perturbatively normalizable. But Weinberg had an idea in 1979. Okay, the theory is not normalized, but you put a cutoff, I mean, in the ultraviolet. You don't count all the modes. You put a cutoff on the ultraviolet modes, and you calculate all the coupling constant if as function of this cutoff. And once you calculated all these coupling constant as function, you send the cutoff to infinity with the hope to find what is called a fixed point on which you can normalize the theory. So the theory is perturbative, non-renormalizable, but could be non-perturbatively normalizable according to the principle of non-perturbative normalization of Wilson critical phenomena. So essentially, I show you the the action of Einstein general relativity. Essentially, you put for the gravitational constant a factor that it's not anymore the gravitational constant. You at quantum level is variable, so you can have a stronger and a weaker gravity, and in this space of parameter, you try to find an asymptotic surface on which you can normalize the theory, because you suppose that the quantum theory, the gravity is not anymore constant. This is the idea. And this method seems to work because they were able to normalize gravity in some cases. Okay. Conclusion. A well-established quantum theory of gravity, as you probably have understood in my attempt to explain different approach, does not exist yet. We have canonical quantum gravity, the Hamiltonian approach, that is the more traditional one, but nobody was able to find no solution except Arthur and Hawking. Loop quantum gravity, there are mathematical problems. String theory, no supersymmetry found. Quantum Regge calculus maybe can give an idea of how gravity works close to the Big Bang singularity. Asymptotic safety is quite young. They have a computational problem because in order to solve to solve the problem, they have to do what is called truncation, and it's not very mathematical sound. So more work seems needed for gravity. One of the problems is that we do not have, as you know better than me, we have this barrier of microwave background radiation. Below this barrier, we don't know anything. So insight from phenomena are missing. Okay, I stop here.
Thanks, Gabriele. And if there are questions here or online, please unmute yourself and ask the question directly.
I have a quick question later.
Ok. Michele?
Sì, c'è Oscar.
Ok.
Oscar.
Oscar
No,
sta here. Oscar, please go on.
Okay. No, just I don't know if it is a question, probably a question and a comment at the same time. Concerning string theory, no?
The more famous approach.
Yeah, you said that this is ruled out by the non-discovery of supersymmetry, no? The string theory implies
too
supersymmetry.
strong. Yeah, you are right. I'm being too harsh.
Yeah, that exactly. This is the question, no? Probably the LHC experiment have ruled out minimal non-string theory, but maybe
right.
that
Minimal supersymmetry is ruled out. Yeah,
it's in any case an unlike solution, no? The fact that we need an even more complicated theory, but in principle is still there, no?
Yeah.
So you agree
with
that?
I should say in a more correct way, minimal supersymmetry has been ruled out, or we need more energetic accelerator, higher energies. But you are right. You cannot say that everything is ruled out completely.
Yeah.
No, you're right. I agree.
And a more general question is that any theoretical hypothesis at the end needs confirmation by experiment or since we are astrophysicists from observations of star galaxy and so on. So the question is how we can probe this theory, this quantum theory, quantum gravity.
you are right. This is a failure of quantum gravity. We were not able up to now to propose any experiment based on which we can falsify the theory, so to say, because we were not able to say. I have seen, to be honest, very interesting work regarding entanglement coming from quantum gravity, but I don't remind very well. But there are attempts by some groups to propose some experiment based on quantum gravity entanglement, but I don't know much to be. There are attempts in this direction, but what you are pointing, it's very true. One of the failure of string theory and other theory of quantum gravity is in all these 50 years that is, the theory and the attempts are going on, we were not able to suggest any experiment based on that to verify the theory or to rule it out. Yeah, you're right. This is unfortunately one.
Thank you,
Okay,
Oscar.
Many thanks. Okay.
Oh, thanks for the talk. A very, very naive question.
Yeah, the next question, the best question. Because
I
very important question.
I have a great question. So, would you mind just confirming my understanding? You were saying we have no way to falsify the theory.
Yeah, we don't do with the experiment.
I think the only proposal that we are aware of, I think I learned from Carlo Lendi, was about the search of white holes seen as a consequence of the quantization of space. So if you, if you just like if you think about the black hole like a collapsing star, an ongoing collapsing star, somebody will give the fundamental quantum space dimension, and at that point it will collapse back. While this process is instantaneous from the point of view of for a matter, the time is so inflated for its observer, so it would take a very long time scale. And so I think there was this idea of searching for white holes, and then for the
white holes.
White holes, yeah.
I don't know much.
So that's it. What this will only happen. Yeah, this will only happen if space is quite quantized. And the problem is the universe too young to see any? My question is also, would we, even if these things exist, would we be able to recognize them, to distinguish them for whatever else, supernova or quasars?
Yeah.
Do you know anything about?
No, to be honest, I'm not. I don't know much about this later proposal by Carlo Rovelli.
I think it was just an idea, like
I have heard this proposal of light coming from distances. The only thing I have heard is that there was this experiment. If the space-time is quantized, if it would be continuous or discrete, this could give two different results. But I think that they do the measurements and the result was the same. And so
okay. Thanks.
I also have a question. Okay, of course, I'm not expert at all of the topic, but I was wondering if measurements with the next generation gravitational wave detectors of the gravitational wave background from inflation, let's say, might help to disentangle the uncertainties between all these different theories. And in general, like if you had to make a bet, if you think that the problem will be solved first from a theoretical point of view, or thanks to a hint from data?
this is an interesting question because what I know, but I'm not an expert, is that inflation is driven by quantum oscillation. So new results on inflation, and you know that also inflation is not anymore, it's even not as well tested yet, because anybody assumes that inflation is the only way we have to explain the fact that the temperature of microwave background radiation is the same everywhere. The only mechanism, you know, it's inflation, but still there is no proof in what I have seen of the real inflation is the right mechanism. Anybody say that it's okay. But what we know is that inflation, it's driven by quantum oscillation that comes from the quantum phase of the universe. So in my opinion, this could be a first step toward a better understanding of quantum gravity. A better understanding of what, because yes, if inflation is right, should be driven by quantum oscillation of the early phase, in the quantum phase of the universe. So it's not the solution of quantum gravity, neither is the phenomena that we are looking for quantum gravity, but at least could give some hints.
Thanks.
Thank you.
If there are no other, fine. Okay. If you,
Just a quick question. I was thinking about what Umberto said
Yeah,
about the observables.
observables in quantum gravity.
Yeah, I was wondering if it's a matter of sensitivity or instrumentation. I mean, if
Ah.
you want to see, you was explained that some experiment has been done probably from light coming from the period.
Yeah,
No difference has been mentioned, but it could be still a matter of are we able to see the difference? This is the
unfortunately, as you see here, the Planck energy 10 to the 19. That is really too much even for LHC. It's a science fiction to think an accelerator of these energies. The problem is sensitivity, yes, but that would be really an experiment that at the moment it's science fiction. We cannot reach this energy because it's a length of you know, the Planck length. Planck is 10 to the minus 33 centimeters. I said before. Yeah, 33 centimeters.
so then my question is probably connected to, and it's the doubtless obviously. So this is something related to what Eleonora said, but on another perspective, not from the perspective of gravitation, but from the perspective of light. So the CMB. So one thing that we probably say at every event when we talk about the early universe, we say, okay, that no, we say that the structure of the universe grow through the original quantistic fluctuation.
Yes, true.
So we say that every
I say that too.
every time we have a public outreach event, we speak about the early universe. So it means that the quantic level is embedded into large scale structure of the universe.
Yes.
And so the tiniest scales we're talking about, they obviously they have an impact. But so the point I'm understanding is that there is no experiment, no idea, or no connection that we can find yet, even at the CMB11, which is, you know, the earliest we can see. So what is the real limitation for that? Why? It's no, we are talking about from the theoretical part.
No, what
After all, it has an impact on the larger scale universe.
yeah. My way of seeing what you are saying is that you have galaxies, my point of view, because you had variation of the gravitational field. So in some point, if I read well, you have that gravity was stronger, so you have accumulation of matter in some point, and this is the reason for which, if I understand well, it's my understanding, you had a quantum phase of the universe that was quantum. I don't know if someone is trying to do any research based on that. Only once I asked if there could be a correlation between CMB and the structure, the how do you say, the structure of the universe.
Large scale structure.
Of the large scale of the universe. But a famous cosmologist from Cambridge told me that according to him, there would be no connection because you have a sort of smoothing of the function, because when you have the expansion of the universe, also because of the inflation, everything has been smoothed out and there is no correlation. What I understand is that there is only this thing that this is related to a quantum phase of the universe, but the correlation has been smoothed out because of the inflation that smoothed out everything. Is what I have heard. So I don't know, but if there is someone that is, if I read well your question, someone who is trying to make a connection, the structure of the universe, I mean, why the matter is concentrated at some point, and the original quantum oscillation of the field. But I have no idea at all. It's not my field of research. Probably somebody has done something.
Probably is that now you see that everything is homogeneous. So if there was some difference at the beginning when they formed, they could be considered out.
Yeah, because this is, it taught me
Is this.
this famous cosmology died.
George just from Zeno. Okay. Vabbè. So there are no other questions. Vabbè, thank you, Gabriele. And next, Enzo.
Oh, thank you very much.
Ciao, Enzo.
Thank you very much. Thank you.
Now, let's stop the recording and we meet again if I manage to stop it.
Yes.
We meet again.